Ya, terima kasih atas kesempatannya Ibu. Izin untuk memulai presentasi dengan bahasa Inggris. Good afternoon, honorable lecturers, to my advisor Prof. Moses, and today's examiner Bu Evi and Bu Dana. Today I'll be presenting my final project results in this presentation titled Design of Defect Detection System with Real-Time Surveillance on Pilfer-Proof Caps. Before we go on to the results, I would like to briefly introduce on our object of observation for our defect detection system, where the system will detect bottle caps, specifically pilfer-proof caps or PP caps addressed within this research. And PP caps are usually used in pharmaceutical and F&B industries. Hence, its production is under strict regulations, such as the ISO 22000 and ISO 11607 is in this slide. And additionally, within this slide, there's an additional standard that has been set by the Bottle Cap Manufacturing Co., which is the observed company, in which there is standard defect that is formulated for classifications of defective PP caps within the company. For the production process itself in pilfer-proof caps, as shown in the flow chart here, there are several processes of shaping, and in additional, they have also implemented quality management steps for random sampling and online inspection, where pilfer-proof caps are inspected manually as of for now for its defects. And here is a visualization on the production floor of the pilfer-proof caps production within the pilfer-proof line of Bottle Cap Manufacturing & Co. And for the existing condition, first on the target of the company. The company has set a specific target of 90% quality inspection accuracy for each caps. And for now, for the existing condition, there are several issues that make this unable to reach more than that 90%, which includes the online inspection, where there are issues on the operator's working time and the overwhelming rate of production for PP caps. Meanwhile, for the offline random sampling, which is done in the end before packaging, there is insufficient sampling size and risk of sampling bias. These issues causes high rate of return and thus high loss towards the company's profit. With such observation, the problem statement for this research posed that the existing quality inspection is deemed to be inaccurate and also ineffective. Hence, we have the urgency to create an accurate defect detection system based on the company standards that will prevent continuous disruption on the subsequent manufacturing processes and prevent compromised product integrity and consumer safety. For the research, there are three objectives, which is development of deep learning model to track and detect defects in PP cap, development of real-time defect detection through the deployment of web camera systems, and lastly will be the testing and evaluation phase of the proposed system. For the research scope, there is two limitations that is placed, which is the evaluation of PP caps are limited to brand reported with highest number product complaints and return within the year 2022 to 2023, and defects that is to be identified will be generated based on the standard defect table, specifically to the exterior of the defect caps, of the PP caps. And for the assumption, Bottle Cap Manufacturing Co. plays a role as a normal bottle cap manufacturing company in which its line and technology will remain consistent and unaltered during the research progress. For the benefits, we hope that the adoption of automation within the quality inspection will increase the accuracy and consistency alongside the reliability of quality assurance within the PP cap inspection line. And additionally, the integration of the defect detection model in the quality inspection line will enhance the productivity and also efficiency of the company. Here is a short introduction on the types of defects, specifically towards the exterior. And within this research, we don't address all of them. some of them are addressed for the defect categories that will be learned by the model. But here we can see that the visualization where some of the defects are not shown or represented throughout all of the perspective. Hence, within this research, there will be a multi-view surveillance implemented, focusing on the top, front, and back of the PP caps to see the representativeness of the exterior condition of the PP cap. For the model that will be integrated within the system, we will use 4 models of computer vision, which is ResNet 50, MobileNet V2, Faster RCN, and Angulo V5, where this model will be then modified with improvement modules to improve the performance of the model and compatibility towards the detection of defect. These improvement modules are all based off prior research on implementations and case studies similar to the current research that is done. Additionally, we will implement confidence in threshold, where it will be calculated using a statistical approach with ROC and Uden index methodology. And here's some of the implementation of transfer learning computer vision on industrial setting, where we also will integrate within the training process of the model. Now onto the methodology itself. The methodology is divided into 5 phases, which starts with data acquisition or dataset collection, and data classification, which is prepping the dataset, machine learning model improvement, where we will compare the training and validation results of the 4 modified and improved models, formulation of real-time defect detection design, where we will integrate software and also hardware modules to create the overall real-time defect detection system. Additionally, gauging the confidence threshold, where we will use RC and Uden index as a statistical approach to find the optimal point of confidence threshold. Now onto the research results and findings. For the first phase, data acquisition, I've managed to compile 100 defective PP cap in the company with the same brand, and take manually picture taking 300 primary defective PP cap images from it. And then we integrate further for increased variety of the dataset with 923 clean secondary images that is sourced from a secondary source, which is TNG. However, there is a consistency within the dataset where all of these PP caps share the same dimension and type, just different brand and also different colors. And for data classification wise, from the input of the dataset collected, we will do several processing. Here are several of the processing done: multi-label annotation, image resizing based on the desired width and height dimension required for each of the model, and augmentation. The result will be a series of pictures in GPG format and annotation coordinates in CSV. However, within this phase, we identified an issue in which, because the nature of the dataset is multi-labeled, hence we have gathered several defect categories that are of an uneven distribution in amount. Therefore, we have done an additional step, which is erasing some of the datasets annotation for defect categories to ensure that all of the defect categories number of annotation is even for a better training process. Now on to the third phase, which is machine learning model improvement, or the comparative study of the result in training and validation between the 4 models, where during the training, after inputting the dataset, we have also tuned the model for its training process using several hyperparameters, which is epoch, learning rate, and batch, with such methodology as listed in the slide. And for the validation and training process, results can be seen here in the graph and also in the table. For the validation itself, we use the results to find which of the models will be selected and then integrated to the software of the system. And in which here there are several indicators. One of them, the category, lies on the performance indicator, and then the other is the target that has been placed by the company. So for the performance indicator itself, we will focus on accuracy, recall, and precision, while the target that the company has set is inference time and accuracy. inference time is benchmarked based on the amount of time taken for one PPCAP manual quality inspection. So it should be less than what is benchmarked as 0.5 seconds, while accuracy is based on the target that the company has set. And as shown that the only model that qualifies for all of the criteria is improved YOLO V5, which then we move on to the next phase, the formulation of real-time defect detection design, where hardware and software modules are integrated to create the overall system. So the saved models and also the weights that has been trained prior will be integrated to the back-end and front-end files of the local dashboard that is supported by a Flask module. Additionally, for the hardware, there are three categories of the hardwares, which is surveillance device being 3 web cameras, 1 adapter, 1 set of environmental control box, and the processing system unit, which is a laptop. And as shown here in the diagram, there is the assembled setup and the result of the UI dashboard on the local server, local dashboard server, as shown here, tracking the defects. The additional module of environment control box was carried out or was implemented due to the systems itself being prone and sensitive towards external factor changes. Some of the reasons are here, and these factors really influence the performance of the overall system. Hence, that is why we decided to create an environmental control box to be able to enhance the performance of the system despite all of the in all of the environment it is going to be placed. For the fifth and final phase, which is gauging the confidence threshold, this assembled system will be then tested into the production line, where the data set is of the PPCAP here shown, which is differ in color and brand from the data set of training and validation. Hence, in the testing, there was a lot of false positive detections. However, this data is used to calculate the confidence threshold because it also considers on the model robustness in dealing on data sets that hasn't been inputted within their training and validation. And as shown here, with the maximum value of Youden index being 65%, and the local optimal value of the ROC is in 65%. This means that in 65%, it can balance sensitivity and also specificity of the overall system. For after that, finding 60%, we have implemented directly into the system, and we did another comparative study. So prior the data collected prior the implementation of the threshold, and after we test again with the threshold, as shown here, most of the performance indicator is better after the threshold implementation. This is because the threshold was able to filter out false positive detections due to these causes, the discrepancies of the testing and training and validation data sets, lens detection, and point of contact detection between two PPCAPs, which rather has a lower confidence inference in comparison to actual defective traits of the defective PPCAPs. Within this study, we have founded several findings, one of which the expanding data set with varied cap colors and design is required to enhance the model's ability to generalize and also to be more robust. Additionally, for the second point is that lens visibility and cap contact points is regarded as something defective by the model, hence false positive detection. Thirdly is the importance of Youden index to calibrate and find the optimum point of confidence threshold, because as shown here, it was able to obtain the best performance matrix from comparison before and after due to the calculation of the threshold from ROC and Youden index. For another comparative study that we have also done, which is real-time defect detection system that we have created against the manual quality inspection. Here we focuses on the amount of time required to test 10 PPCAPs, and as shown within 3 iterations, there is a consistent improvement or reduction of time where 19.33% of time is reduced from the use of automated quality inspection. Here we can see that the findings within this comparative study is that the improved ULO-V5 model in prior studies too supporting it can cope up with the dynamic production condition and the rate of the production of PP cap within bottle cap manufacturing co. Additionally, the environment control box ensures consistent camera performance and has maintained the system to be in its best condition by reducing brightness fluctuation and standardizing images, preventing distortions. Now on to our conclusion. To answer the prior objective that is formulated within the research study, the first conclusion arrived was that the enhanced ULO-V5 model demonstrated superior defect detection performance on PP cap, proving suitability for high-speed automated quality inspection, and they can also do concurrent processing in multi-view input. Additionally, for the second is integration of real-time web camera system with flash-based dashboard enabled efficient visual inspection and immediate feedback, although there is an additional need of environmental control box to ensure the standardizing of the environment. Third, and the final conclusion is that system testing confirmed that utilizing AI to inspect can, even though it's in the prototype stage, outperforms manual inspection in both speed and also accuracy. Here are several of the suggestions for future studies or further development on the system to enhance the system's performance. That's it from me. Thank you for your attention. But I would also like to add that there are several attachments that can be seen in the next slides within the PPT for future reference. Thank you.